Okay, can everyone hear me fine? Yo, yeah, it looks like it. Cool. Hi everyone, I'm Edo. I'm going to introduce myself a bit more in depth in a bit. First of all, thanks to the social computing chair for letting me do this. It's already the second year, and we try to put this lecture at the end of the semester. I've been told to tell you that is not part of the exam. We just take the chance to look at a topic that we find particularly interesting, and then I take some time to maybe give you a bit of insight of how we work on the same topic in the industry. I am part of Liquid. We're a foundation model company with a bit of an edge specialization, and we're headquartered in Boston. Right, so this is what we now call the NLP Frontier series once a year, and I'm a member of technical staff at Liquid. I've been there now just over a year, and today I come to you to talk about scaling laws. I don't know if these were seen maybe even to like a very small extent in the advanced NLP lecture so far. In case they haven't, that's not a problem. So the lecture today will be split in two parts. In the first part, we'll look more at the general literature on scaling laws, at least like the high level, like the biggest paper that there were, and what is the impact how you can actually use them to predict model performance in advance, especially as you start to go on like the upper end of model size. And then we're going to discuss of how we at Liquid look at the scaling laws and try to translate them in day-to-day things to do for us, especially when we work at the edge. Right, so jumping into the first part, and FYI, all references will be at the end. We'll make the slides available, so no worries. And maybe we'll take, we'll see a bit how the time goes, but we'll take a break after the first part if you have any question regarding that part, and then we jump into the second part. Right, so scaling. Scaling is by far the best thing that you can do for your model, for at least general intelligence. Now, general intelligence is very hard to define, but broadly speaking, I define general intelligence in this very subspace as your pre-training performance. So if you're getting better at pre-training, you'll see all sorts of advantages downstream. That's like the raw intelligence of your model. And then if you have more of that, then you're going to be a bit better at math, and you're going to be better at the rest. And this is roughly what every model company is doing right now. So it is kind of true that scaling is the steroid for general intelligence. So at the very beginning, all the observations that were made about scaling were purely anecdotal. So people started to see, oh, if I just take the same model with no changes, I just train it for longer on higher quality data, I get a better model. Or, oh, if I take Llama 70B or any not completely messed up 70B, there's just no way that a 3B model will get any close, at least like on a plethora of capabilities, maybe on one, but not more than that. So sheer scaling is still the dominant driver in explaining any sort of variance that you can see in model capability. And the phenomenon is robust enough to actually being able to fit specific law that allow to predict what a model can do if we just give more compute, more data, and just like more parameters to it. And this has been showed in a number of papers. The first one is the Kaplan paper, 2020. This was when Kaplan was still at OpenAI. And so this is 2 years prior to ChatGPT, half a year to a year prior to GPT-3. What they did, they simply took models from a few, I think it was like tens of thousands in parameter count, and they scaled up to just over 1 billion parameter. And they looked at, okay, how does the loss change as I scale up these 3 factors? And these 3 factors are nothing else but model size, and a good metric for model size is number of parameters. Data size, which is the number of tokens that you've seen at pre-training time. I'm going to say training time from now on, but always assume that it's pre-training. And compute in petaflop days. And the key result from their first work is that performance improves extremely predictably as a power law within these 3 dimensions. So actually the 3 scaling laws, more than one, predict exactly as if you give more tokens to your model to digest, or if you just allow, if you enable more compute, which means you can shard a larger model, or you just give your model more parameters, you're going to see a very predictable descent in test loss. So this is next word prediction objective data set aside. And these are in log scale. So actually, if you were just to plot it normally, you would see sort of like a descending curve. But in log scale, they will look like a line. And as you can see, there's like what's called like the compute optimal frontier that you cannot train a model that's going to be on the left of that line. So the expected training curve is that you start training on your data, you get a quick descent, you're going to hit this line, and then any further token or compute allocation will not give you really any benefit. And of course, like a better model will require more compute, so the line will be more on the right, and it will go down, and it will be able to exploit more data, so it will reach a lower point along the line, but then of course at some point will taper off as the data and compute is sufficient. Of course, for those experiments, if you're scaling one of these specific dimensions, again, compute, data, and parameters, you need to make sure that the other dimensions are large enough so that they're not bottlenecking the one that you're actually trying to scale, right? Before, maybe some of you are here thinking, what the heck is a petaflop day? So maybe let's clarify that very quickly. So a petaflop is just like 3 orders of magnitude above a teraflop. So it's roughly 10 to the 15 flop per second, sustained at maximum capacity for an entire day. So in GPU numbers, we're talking just over 3 A100s, going at full capacity with perfect connectivity for an entire day. So here we're talking like GPUs that are roughly 20, 30K to purchase in a perfect setting. H100s, which is now the standard in the industry, and I think now everyone's switching over to B200s, are a bit better, but maybe it's like just over 3, but not too far. Right, so this is what you would need to have 1 petaflop day. And I think in the Kaplan scale, the first Kaplan scale experiment, this is roughly the scale that they were getting at the upper end. So we can see that the largest models were roughly trained on 10 petaflop days. Right. So coming back to the paper, maybe one of the most interesting thing to see is that sure, we have scaling laws following a power law across like for these 3 within respect to these 3 dimensions. But the more interesting thing is that there's nothing else. Like these 3 factors alone seem to be sufficient to predict what you can actually expect from the model. So there's a general insensitivity to architecture changes. Now, this was still coming off Alec Radford work when they started to scale GPT-2 further. So all they tried really was like changes within a transformer decoder. That's not a huge space to sample from, but still, they found none. So the TLDR here is like, given reasonable choices, architecture doesn't really matter. The laws span over 6 orders of magnitude, so they seem pretty consistent, and there's still no divergence as we look at the upper end for now. Overfitting was found to be the default setting that any machine learning practitioner, almost every machine learning practitioner has worked so far. So data was always the limiting factor. And maybe some of us remember like working on like tens of thousands labeled data set for hate speech. And it seemed that no matter how much larger we made the model, it was kind of the same. And so the overparameterization regime, meaning you have more parameters that you can justify for given the data that you have available, is kind of the default thing. And finally, the training curve shape and expected route doesn't really depend on model size. So as you scale up the model, the training curve will look basically of the same shape, will just be on a better side of that Pareto optimal. The limitation, of course, as I already said, the architecture that they looked at was transformer decoder. That's a pretty narrow space to look at, but so far it seems to handle. The upper end, which was considered huge back then, was 1.5B. Now we know that we can get a lot larger, but so of course this raises the question of, is it gonna diverge at some point as we get like in the tens or hundreds of even, or maybe even trillion parameters size? And then, as I was saying before, the scaling laws, they are measuring usually what happens for general intelligence, which is pretty much what you can get a test loss for pre-training. So the objective is always self-supervised next word prediction. And although the increase, like the performance boost that you get is very predictable, does that really transform in any performance downstream? If a model goes down very predictably in pre-training, maybe like the math performance will be like very unpredictable and it's not going to scale so predictably. So what's going to happen for downstream task? And a bit of a weird choice for that paper, they did not count embedding parameters, which for a vocabulary-based task feels a bit weird when you're trying to fit coefficients, but for like works later on fix this. Okay, so going further, where the 1.5b, they have what was then GPT-2. They take GPT-3, they go up 2 orders of magnitude and still falls on the same line. So it seems like we can actually, you know, go up and up in the size of model, and the scale still, and the loss still holds. And what was the most notable emerging behavior when having a model that does this better on pre-training loss was the fact that a few shot emerged. That was the first time around. So we know that around the hundreds of billions emerges under these training setting. The question is, okay, you're talking about transformer decoder specifically being trained on a pre-training loss for language modeling. That doesn't really sound any universal. So the first question is, okay, does this apply to any other modality? And the answer is, as long as the task is autoregressive and you're in the same architecture pool, yes, they're pretty universal. This was still a paper from Kaplan. Sorry. This was still a paper from Kaplan, and what they realized is for other modalities, they had to subtract a constant to basically make the law fit well, and they started observing a sort of a curve. So it means that your performance gains are tapering off as you're scaling up the model. Interestingly enough, language modeling is the one where the gains are still looking pretty linear, and again, we're linear in log scale. So any boost in those dimensions, you're getting log level returns. But still, it doesn't really seem to flatten out. So a question would be, can you actually get to 0? I mean, we know that you can't because it's a statistical task, so you cannot deterministically predict the whole internet, but you know, so far the whole seems to point us that way. So there's a task entropy, so this irreducible term, which is in those graphs what would be like an horizontal line that you will tend to and that you can not possibly get better of, at least for specific autoregressive tasks. But there's still no meaningful estimate for language modeling. So the language is still the law that has no constant that needs to be subtracted in order to get a perfect power law. This changes with a paper from Google that came out a couple years after, which I call Chinchilla, just after the model that they proposed, where they followed the same kind of experiments that Kaplan has run, but this time they just go a bit larger in model size. They move the upper end from 1.5b to 16b, so that's 1 order of magnitude more, and they start counting embedding parameters. And we do start to see some flattening as well in language modeling. And the suspected reason for why flattening happens so much later for language modeling is just like the availability of data. You will just not have enough VLM data that will match the size of pure text on which you can do self-supervised learning on the entire internet. And so that's why we estimate that they had to scale so much before seeing any sort of tapering off. Right, so Chinchilla moves up the scale, they see some tapering off. What is the implication? They find that all the large models that were trained so far, and at this point we know that the largest was GPT-3, was undertrained. meaning that there were not enough tokens for it to actually fully exploit and get to where it could have been. And in the Kaplan experiments, when you remember I was saying before that you need the other quantities like compute and data to be extremely large so that when you're scaling the model, they're not bottlenecking you. But the estimate for that quantity were 300 billions, which seemed like an absurd amount back then. We now know that that's a very small amount. And so while Kaplan just fixed that amount as a non-bottlenecking for the data dimension and just scaled the model, we now know that you actually need to scale the data a lot more. And so the Chinchilla paper comes with this parametric law formulation, which is now we can finally base on an irreducible term, which will be the entropy of natural language, plus two terms, one that will depend on the parameter count and one that will depend on the number of tokens available. They do fit two numbers that best represent their curves, but generally speaking, the different tasks will have slightly different laws, and you can just change the two exponents to get optimal fitting for your setting. What also changes is that with the next law, we have a new compute optimal model scaling. So for Kaplan, the exponent was like roughly 0.73, which doesn't really mean anything to us right now, but that's basically how much should you scale your model based on the compute that you have available. But now since Chinchilla, we know that a lot more compute has to go over time just to basically ingest a lot more data. How much you should scale your model actually goes down quite a bit, and you should just have a smaller model training for much longer. How do they prove this in the long term is they say, okay, they've definitely, the larger GPT-3 models and so on, they have left gains on the table. Let's take a 70B, so a third to the half of the existing large models back in 2022. And we just train it on 1.4 trillion tokens, so much longer. And result, they got better MMLU despite having a much smaller model. So this is confirming that everything else was undertrained. And as of today, Chinchilla laws are still the guiding law for estimating next pre-training runs. So whenever you're about to compute anything between tens of thousands to tens of millions to a specific pre-training run, this is roughly how you estimate how much data needs to come in. And usually you do like to overshoot a bit because you don't want to waste a training run, also because they're pretty hard to resume. Yeah, so Chinchilla is now the standard. It was used by Llama, Gemini, pretty much anything that came after. Right. Interestingly enough, one of the largest training runs that was done after this was the GPT-4 training run, where they knew, so I think they initially estimated something in the tens of millions of compute allocation, ended up being 100 millions. And so of course, like before you justify ramping up a cluster like crazy and throwing this much amount of money at it, you want to make sure that you have some expectations and the loss that you're gonna get out of it. And so they did predict quite accurately the training loss that they would get out. And they did this just by fitting the previous runs on the power law that they saw before. And with the second largest run actually being 100 times smaller than what then ended up being GPT-4, the estimated petaflop days that they had to throw at it was 200,000. This is not an official value. The GPT-4 report doesn't disclose any compute utilization. This is more like the leaked value that we all hope is correct. Right, so this is a very good example of how a large team has to do these estimations before committing compute. Right. One last paper that I think is quite interesting regards the amount of data. So amount of compute is very deterministic. The more GPUs, the more flops. Number of parameters, as long as you're counting everything correctly, pretty deterministic. Number of tokens is not a great metric if you want to just account of how much data you're ingesting, because you can have incredibly high quality data, maybe you know like a 1 billion high quality tokens, and then you can have just 1 billion times the letter Q, right? And there are subreddits that just like post the same letter over and over. I don't know why they do it. I'm pretty sure some of them do it to mislead, let's say, training runs. We have to filter heavy for those kind of data, for that kind of data for crawling. But so sheer number of tokens is not like, it's something, it's the only thing that we can measure, at least when broadly crawling. But of course, it's not something that, oh, we should use in the exact mathematical scaling law. So the rule of thumb here is, if you were to train on the actual most informative samples that you have available, you would scale much faster than the power law that was reported so far. And you can go from the power law to an exponential decay, which has a much, much smaller tail, is not as tail heavy. How do you do this? Like, how do you determine whether a sample is informative or not? Well, you need to have a pruning metric. So you need to have some form of metric that whenever you fit a sample in, tells you whether this is hard or easy. What does that even mean? Kind of depends on the setting where you are. So if we take like a very simple classification task, you will have that harder samples are going to be the one closer to the decision boundary, and the easier ones are the one further away. So that distance is somewhat of a proxy. For language modeling, the perplexity that a much larger model has is some sort of a proxy. And once you have these metric that discerns between easy and hard, you can find that for, if you have not many, so in the order of like one data, one example per parameter, then you'd rather discard the hard samples and only keep the easy ones, so at least you can learn something. Whereas like as your data becomes more and more abundant, probably you can learn very quickly the easy patterns, and you'd rather just train on the hard ones. So that's how you should do the pruning. And if your pruning strategy is optimal, or in most cases close to optimal, then you will see that in the first graph, as per training sample on the divided by the number of parameters that you have, the way your loss goes down is much faster than power law. This is all very nice and theoretical. Finding a proxy is extremely rare. So even in the case of large language modeling, this aggressive filtering does give you a better power law, but it will not bring you to exponential decay. For other simple downstream tasks, it is actually the case. You can find in specific examples good proxy pruning metrics. Right. So one of the questions right now would be, all right, so we have laws since 2020 that tell us, oh, you can actually scale model compute and so on, like in a specific way that you will get very predictable guaranteed gains. Why isn't anyone doing this? And also, why only in 2020? The reason is, it took us some time to get to a recipe that could have actually scaled. Before transformers, you cannot scale RNNs just by sequential ingestion of tokens. Plus, I mean, the hardware was not there. We didn't have H100s 15 years ago. So the right recipe was not there. Now the recipe is there, but even with the perfect recipe, you cannot just take, okay, now I'm gonna go from like 100 GPUs, like 100,000 GPUs, and just expect that everything runs fine. Pre-training runs become exponentially harder as you scale your cluster. Anything beyond 1,000 GPUs gets really tricky, and even the number of problems that you deal with become very, very nit. Like we're talking like network interconnect between two of the B200s in a 100,000 GPU cluster. So these are really, really hard to fix. And then of course, how we observe all this gain in performance to even justify, scaling more, is that by avoiding bottlenecks, which at some time at any point in history has always been either data, and I'm gonna go into that in a second, compute, and parameters. We didn't have models that were actually justifying even being able to train in parallel at that parameter scale. Or even literal bottlenecks in the way you would backpropagate the information throughout the network. So until attention, you had vanishing gradients that were an issue. So very briefly a bit more over this, what were the changes that were done in architecture and so on in order to go from the pre-scaling era to the scaling era. So before, when dealing with RNNs, LSTMs, anything like that, you would always have a constant state, having all the information necessary to generate the next state. And then with skip connections, which everyone forgets about, but they're still one of the most used things in any architecture. And then, of course, attention, having this constant path between any two tokens in your context length is what allows us to, okay, now actually we can backpropagate it. We're actually using the entire network and not just the last two layers. Pre-scaling, we had sequential training. Recurrent neural networks are the go-to example here. Transformers can actually ingest sequences in parallel. Limited data was the case until we started to have pre-trained networks. And I think the first one that really started scaling a bit better was BERT, where it was like masked language modeling. But in a general sense, we started to do self-supervised learning, just a next word prediction. Language modeling was not really a big of a thing until then, and we would just like fine-tune from scratch models on very specific use cases. So we were relying on tens of thousands of labeled data, hopefully by an annotator that knows what they're doing. And finally, while we were on a couple of GPUs, the solution is just to get more, better GPUs and with larger clusters. The new trends that we're now observing as we're trying to move beyond the pure scaling era is, or like what we call the GPT type era, is that from transformers, people are trying to move a bit forward to try to avoid the quadratic cost that you have in inference for transformers. So SSMs are now starting to be a thing. Hybrids are starting to be a thing, and we're going to talk about that later. Self-supervised pre-training has the limit of high-quality data that you can possibly crawl from the internet. And like Ilya said a few months ago, we have but one internet. So how do we keep scaling data beyond the size of the data that is available in the open? The answer right now seems to be that you can just like verify the result of a task and through reinforcement learning give feedback to the model. So if you imagine like a code base where you're trying to generate code, and this was extensively used for Claude 4 and I think even Claude 3.7, you can just let your model generate the code, and then this will go through some unit testing that you will have for your code bases. And if the result is correct, this is a good signal. If not, this is a bad signal. And the model can just go at it as much as it wants. It's not limited on any data set anywhere. The result to large, the solution to not large enough data sets is even larger data centers. So that's an easy one. As you can imagine, the compute is by far the strongest bottleneck that we have so far. Most university chairs have no GPUs. Some lucky university chairs have 1 to 10. And then we have most companies, there at least that work purely in AI, that they scale to the tens of thousands. But again, as a power law, like the number of companies that actually have this kind of compute goes down very, very quickly. We know that OpenAI is somewhat in the 100K to 150K compute right now, probably much more very soon. The largest single GPU right now on Earth is Elon's. He's put it up in 19 days, which is impressive to say the least. And we're talking starting to building a power plant next to the data center to power it, that being too slow. So bringing mega batteries over from Tesla to make the power delivery smooth enough so that the whole thing could run, just because building a power plant is not fast enough. So this is how much people are actually rushing at this. There's actually a larger compute resource, which is Google's, but that's distributed across multiple centers and it's actually TPU based. So it's not an apple-to-apple comparison. Elon still has as he claims, the largest one in a single place, which is correct. Everyone is rushing towards the next generation of data centers. The smallest of this next generation that we're aware of will be 200K GPUs, so exactly as the largest right now. We know that Meta and OpenAI are roughly in the half a million GPU plan, and Elon has said he will manage a 1 million one. I think there's a chance that he will actually deliver. And interesting fact, these data centers will be in the gigawatt scale of energy consumption. We're talking more than most cities at this point. I think right now there's like a single-digit percentage, like 2-3%, that we know is of a country's electricity going to pre-training. We estimate that being double-digit very soon. Other funny fact, there was a leak in the PyTorch code some months ago where there was this torch.powerplan.do-not-blow-up function that was found in some of the docs, where you can imagine when you have so many GPUs and so many power and cooling delivered to a single spot, as your pre-training runs is coming to like you're finishing, or even imagine like gradients need to be accumulated and parallelized across a huge number of GPUs, the GPU consumption will go down. And when you have like 100,000 of GPUs that go down in utilization, you suddenly have a spike in the energy available. And this can very easily blow up an entire data center. So their Meta is planning to add in Torch functions that will keep feeding your GPU's fake numbers so that we don't blow up the data center. So this is roughly, I wanted to give you an idea of like what's the scale we're looking at going forward. And then why is everyone trying to find, like what is this entire vibe of, oh, let me find the universal law or like entropy of a specific task? Is either just like physicists in every single paper that talks about scaling law. So that was a good find. Right. So this was the end of the first part, where we talked a bit more about scaling for general intelligence and also implication on going forward. We can do either questions now or just like go through the end and take them all at the end. Is there any preference? Default, I'll go to the end. Okay, I'm gonna drink. Lovely. Okay, so the first part, we were talking how, yeah, scaling is the thing that you should be doing. There's no doubts about that. But that's true for general intelligence. And one thing that we've asked ourselves is, do you really need a model that is good at everything all the time? For frontier research, probably. Like, it doesn't need to be good at everything, but it needs to have definitely a decent level of general intelligence to be able to carry research. And so, yeah, frontier research does require a frontier model. Intellectually very hard tasks, and we're talking like very, very large code bases with a constantly changing documentation online, possibly, especially as long context, as context gets very long. But for most tasks, no, not really. So we know that on specific tasks, and there will be a paper in the references, SLMs or small language models can match models roughly 1,000 times larger. So you can have a 1B model on a specific thing that is roughly as a trillion parameter model with few shot, of course, with given customization. And also these models can run on edge on a specific device. And so there's no API call, there's no internet connection needed, there's no sending over data to some server in some place, and there's no huge cluster going crazy. And for us that work on models on edge, we were like, okay, what does this mean for us? So we have a different model development than these like scaling decoder, transformer decoders have. So we don't really have a recipe yet for architecture search. We do have a recipe for pre-training. The scaling laws apply regardless of order of magnitude. So for pre-training, we can just take the chinchilla laws. We have our small adaptation based on our architectures, but roughly that's followed quite closely. We can just overshoot with data quantity. We don't want to finish a pre-training run and just thinking, oh, if we just had 1 more trillion tokens. And of course, like aggressive filtering on quality, especially on small models, will give your pre-training run much faster convergence. Post-training, still to figure out. We'll talk about it in a bit. And for deployment, what we found is just make it optimized for the hardware you want to run on. And this is our internal stack. So as long as it's fast and easy, it should be good. Right, so talking about architecture search, what we know from the literature so far is really only that the architecture doesn't matter if reasonable choices are made, which is true, but what is a reasonable choice? So as long as you use attention, at least in decoder style, you're safe, and there shouldn't be anything that goes wrong unless you've scaled one of the model dimension extremely weirdly compared to the others, but that's really hard to mess up. But you get quadratic inference, so that's not great for edge, especially. You have other operators that you can include. So you have SSMs, which was like the lecture from last year. You have short comms, hyena style comms, and all of these have subquadratic inference as long as the kernels don't get to the sequence length size. But this is a lot of custom work. Like the entire set of tools and frameworks has been built on attention because everyone was using it. So you have a lot better metrics, but you have to do more work. And then also reminding yourself that a lot of hardwares are memory bottlenecked. So that's the case for phones, where the memory is not much more than the compute that you have available. Whereas like you have some servers that have a lot of memory available. Even cars actually have a lot more memory available than they have compute. And so you can imagine that on a memory bottlenecked type of device, you would rather have a dense model, so all the compute that you have is not going to be more than the memory, so you should just load the entire memory, and you should just load the entire model, and that's it. For hardwares where you have the compute bottleneck, so you can load a lot more in memory, like a lot more experts in an MOE setting that you can actually load on chip. Architecture search is a pretty complex space. There are lots of choices. The very first one was RNNs, nice linear autoregressive generation, but the ingestion kind of is really bad. And plus vanishing gradients, it's just a killer. Attention ticks all the boxes, except is really slow. Convs, they are actually subquadratic, as I was saying before, as long as your kernel doesn't extend ad infinitum. And they do parallelize very well. Of course, the context that you have available is it cannot be larger than your kernel just by definition. SSMs tick theoretically all the boxes, but they're really hard to implement. And even a lot of the theoretical gains are really hard to get in practice on each hardware at the same time. So what we did is, there doesn't really seem to be a right architecture for each single hardware. So let's go custom hybrids and try to figure out a response for type of hardware or type of bottleneck. And this is how we came with this paper it was out since a few months at iClear, STAR, Synthesis of Taylor Architecture, where we take existing architectures, and a few examples could be like a transformer, which you can just imagine as a backbone of attention blocks, and then of course like feature mixers or FFNs or swigglus for just mixing features in the middle. And then you have striped hybrids, which would be models that have two type of operators, so that can be like Mamba together with attention in a striped way, so one block after the other in alternation. And we start to do heavy mutations on the several operators. So assuming the backbone staying the same dimension, we start to take out operators and putting others in. How do we do it? We just do it randomly until our properties, which is like cache size, number of parameters, and performance, which can be perplexity on very short pre-training data sets. We're talking like tens of millions, so like nothing compared to a full pre-training run. So we just keep repeating until we're happy with the performance that we get from a specific model population. Then we just do more random mutation. In practice, you just take the best candidates, you mix them up, and then you do random switches, and you keep iterating. So this starts to give us over time across population better architecture candidates. And one example that I wanted to bring today is the Hyena Edge, which is also what I'm going to go and demo later. So in this case, we took the metrics from an S24 Ultra, and we just wanted something that would be a lot faster at pre-field latency, decode latency, so pretty much how how fast can you get a prompt in, and how much faster can you decode the response, as well as like memory usage, because obviously you're running on a phone. And yeah, so in this case, we ended up with a hybrid that had a lot of short convs and some, I think, 6 attention layers out of 24. Sorry, out of 16. And this is what at least was very easy to implement for us to run on phones. So to conclude the star or architecture search part, now we do have a recipe for architecture search. We do have a recipe for pre-training. We're still missing the post-training one. So, and that's where really all the scaling laws, they go a bit out of the window, because all they mean is like this, all they can predict is this general intelligence. They don't really tell you how the downstream task will evolve. So we don't know anything there. And so far, the empirical result is that specific model capabilities, and that can be creative writing, coding, math, will still very much depend on the data mix that you feed the model at post-training time. The smaller your model is, the more you have to be careful with data mix, just because of limited memorization capability. So if you have like something in the trillions, it's really hard that you saturate with tokens your model. But of course, if you have a 1 billion model, if you feed a lot of code, it will very quickly get worse at math and so on. But for us, that's okay, because small language models, so they don't have much memory capacity to begin with, but you wouldn't want one model that does everything. You would just like many small models that do a couple of things each very well. So rather than knowing a lot, you would just to go and execute on the one thing that it can do. And we started prioritizing instruction following evals a lot more than knowledge eval. So the classic eval that everyone looks at, it was MMLU. So this like quiz style, extremely large scale data sets where you could ask your model questions and you would need to pick the right option, which is very, very knowledge heavy. And we started just like measuring evals like IF eval, where there's a large variety of instructions that your model has to follow, be that also structure output on math, and then it exactly has to execute, even if the context is actually provided in the prompt. And then for any further customization that we want to do, we can just take the post-trained checkpoint and then apply task-specific eval. So if you have a medical use case where they say, oh, here's a PDF from the patient, here's the OCR result, I want the exact metadata extracted in this specific way, then you would of course do like a specific fine tune on that, which is not going to cost as much because your model is rather small. Right, so putting it all together, we do now have a recipe for all the things in the pipeline, and the result of us putting all these things together was LFM2, which is the model that we released just last week, which is very good in quality, at least compared to models of the same size. We still know that for general intelligence, the scaling laws apply. The main contender that we were against was Quen. And what we were mostly interested in seeing is decoding time on CPU because of the hardware that we want to run on. And there are three sizes at which the model is out. There is the largest, which is a 1B, which however does perform on par with a 1.7, or at least with the best 1.7. And then we have smaller models that actually run even faster. Of course, that you'll have some decrease in quality, but speed was what we wanted to prioritize. Right, so these are like the two main metrics. The models are in Hugging Face. You'll get the link if you want to look at them more. And yeah, I think now we can demo maybe one of them. So the first demo is just, this is the model living on our server. So this is actually running on GPU, right? I'm actually going to do an API call. And looks like a normal chat. So we'll just ask, hey, hi, I'm doing a lecture about scaling laws. What insights can I give the audience to keep them engaged? Something like this. And now the call is off, and the decoding speed is pretty fast, right? So this is, again, as on a single H100 inference. You can probably fit more of these models on a single H100. Usually the batch size that we can afford for even post-training is 128. But the other, I'm actually gonna copy the prompt just to not write it twice. Is this internet connection off? Oh, there we go. So this is a Hugging Face space. You can also access it as public. Are you guys familiar with WebAssembly? No one. Okay. So WebAssembly is just a way of compiling code for your browser. So right now, these models, the 3 LFM2s that are downloaded here, they're running locally on my machine, but they don't even know what my machine is. So the cool thing is WebAssembly compiles the models for your browser, and then your browser compiles the models for your device. So the browser knows what your device is, but our stack doesn't. So this is pretty much a stack-free local deployment of our models. And let's maybe take the 350M. So this is now running locally on CPU. It doesn't really use the fact that I have a shared memory on the Mac. But yeah, so this is speed on CPU. And this is a 350M model, so roughly at the BERT large scale. And this is only fine-tuned for general chat. Yeah, of course, like as I said, like we will have different checkpoints depending on the task that we would fine-tune for. Right. This was it for the lecture. Here are the references. You'll get the slides, don't worry, you don't have to copy anything. But what I wanted to add was, of course, like the Kaplan-Chinchilla papers, which is like how the whole scaling laws topic started. GPT-3 paper, which is 2 more orders of magnitude plus the emerging behavior of few shot. The GPT-4 technical report, I'm afraid, is very unuseful unless you look at the scaling laws that they've reported. And then the beyond scaling laws via pruning is the paper I was talking about, to pretty much decide that number of tokens is just not a great proxy for at least when you observe like the mathematical scaling laws. And then effectivity of SLMs looks at SLM's usage in a variety of tasks and makes the argument of like why you actually don't really need to scale for these quick executions. And then finally our work, which is a STAR paper and like a plethora of references to wherever you can find our models. Cool, thank you so much. And it's a good time for questions, thanks.